the red arrow, all these are our kx. Okay, all these are our kx. Okay, so net force to net force acting on spring is equal to, right? So there are 4 springs in parallel, so they are minus kx 1, 2, 3, 4, which is equal to minus 4 kx. Okay. So when you write up the equation, minus 4 kx is equal to mx double dot plus by 4 kx, the whole thing will be equal to 0. Okay. So from here, we have x double dot plus by 4k over mx, which is equal to 0. And then finally, we know that the question asks what is the natural frequency. Omega n is equal to square root of 4k over m. Okay. Most important thing, I want you all to be what? Comfortable with what? Free body what? Diagram. That's the purpose. Okay, let's look at another problem. Okay, any questions so far from anyone? Yes. Yeah, and not just that. If you look at the direction also, right? Anything that's relative to the x direction is positive. Okay, so all these are opposing. That is why they are what? They are all negative. Okay. Yes. Yeah. This problem, like what has been asked earlier, this problem has been simplified. Okay, by right, the spring can still be in can be in compression. No doubt it is still in tension, or no doubt it's stretching. Okay. Okay, I like to address this question. 2 students have asked already. Right. Okay. So the question asks, can the spring be in compression when it has been extended? I repeat again, can the spring be in compression when it is extended? The answer is yes. Okay. Why is it possible? If you have a spring over here, and this position that I have drawn, okay, I'm going to draw a vertical line coming down. Okay. So this is at its equilibrium position. i.e., when it's equilibrium, okay, Fs, the spring force is equal to what? 0. Okay. Now, in the next stage, the spring has been moved to a position, and this position, I will call this position L minus by x1. Okay, where the distance from here to here is L. Okay, and the distance from here to here is my x1. In order for that to happen, we have to compress the spring. So Fs is also equal to what? Negative now. Negative because we are inducing what? Compression. Now, what if now the spring is now at this position over here. This is our x2. So now it's L minus by x2. Now, is the spring under tension or compression? It's still under what? Compression. Why is still under compression? So for this case, you know that this is K L minus x1. Or this case is K. You know, to be fair, I'm going to put this is x1 minus L. Okay, I'll tell you why later. It will help you handle the direction. For this case, okay, and for the fact not for the, okay, I'll leave it as there. Are we clear? Okay, so we know that this is under what? Compression, right? Both are in what? Compression. No doubt, relatively is what? No doubt x1 is greater than x2. Yes or no? Right? It's still under in what? Compression. The only way that this will go into tension is what? So now, if the spring gone past is what? Equilibrium now. Now this is your what? X3. For this to happen, you know that Fs is going to be what? In what? Tension. We clear? Okay. Okay, so the next problem that we are going to look at, okay, we're going to look at example number 2. So for example number 2, we have a different sort of problem now. I'll start on a new page. Now, they are a bit tricky. They put the spring in the what? In the opposite direction. Okay, they are being cheeky now. Okay. Okay, you can see that. So the uniform beam is supported at its end by two springs A and B, each having the same stiffness. When nothing is supporting on the mass, it has a period of vertical vibration of 0.83 seconds. If a 50 kilogram mass is placed at its center, the period of the vertical vibration is 1.25 seconds. Compute the stiffness of the spring. Okay. So we are going to try to formulate the stiffness of the spring for this case. Okay. So what are we going to do first? Free body diagram. Okay. So for the free body diagram, again, we declare that is what? Positive. Okay. By drawing that, you declare coming down is positive. Okay. So when you come down, the spring force becomes what? So next we have to construct our free body diagram. Okay. Before I go on, I do apologize. When we read question like that, I did something wrong. Okay, we have to write down what we know. Okay, so we are given that the period which is tau That's the symbol for period, which is equal to 0.83 seconds. Okay. And if we look at tau, it's equal to 1 over what? Am I right? 1 over omega n. Okay, that is our, and we also know that omega n is equal to square root what? K over what? M. Okay. So the question wants us to find out about the what? We know the mass, but it asks us to formulate the stiffness, right? Okay, so we know that. So there are two cases over here. When nothing is supported on the beam, it has a vertical period of 0.83 seconds. Okay, so when this problem is not as straightforward as I thought. Okay, so case number one. Okay, case number one. Without the mass of 50 kilogram, okay, the period is equal to 0.83 seconds. Okay. And we were given case number two, with the mass okay, the period becomes 1.52 seconds. Okay, so this is our system now. Okay, earlier I just read and just go quickly past, which is wrong. Okay, don't do what I've just done. Okay, so this system has so we have to determine the stiffness of each spring and the mass of the what? Of the beam. Okay. So what we're going to do now is we're going to construct our free body diagram. And we know we want our system positive to come down. And then we have attached two springs. And if the load were to be coming down, the springs will be under what? Compression. Okay. So this is the reaction that we are going to get, and this is our mass. Okay. So we formulate net force to accelerate mass. So this is my double dot, and then we also write down net force acting on spring. This is equal to minus K, so I call this K1, K2, okay, K minus by K2y, okay. So over here, did they say that K1 is equal to K2? Same stiffness, okay. So note that K1 is equal to K2 and is equal to K because we are going to, because it was specified that K1 is equal to K2. So for this case, we have minus 2K multiplied by Y is equal to my double dot. Okay, so again, we write out. Okay. Right. So we also know that tau no